have a associative law for addition, and now we're going to show that we also have an associative law for multiplication. Okay? We have a commutative law for addition, and we've shown that we have a commutative law for multiplication. Basically, the structure of addition follows very closely in line with the structure of multiplication. And so all the things that we saw for addition, we're pretty much going to redo those for multiplication as well. So that's what we're seeing here. So associative law for multiplication, of course, says if you have x times y times z, where you've multiplied x and y first, if you multiply the y and the z first, you end up getting the same result. All the different input values associate with one another and give you the same answer, right? And so, if you think back to the proof of the associative law for addition, this proof is essentially word for word identical. We're just going to replace product, replace sum with product. So we're going to let x and y be arbitrary. We're going to let z we're going to let m be all z where the law holds. Then we need to know, first of all, is there any number z? Right? Is there any number in M for which the associative law holds? And it's easy to verify for 1. So we say x, y, z, where we're setting z to be 1, right? We want to see if we can rearrange the parentheses to where we can capture the z on the other side. So what we do is, we know z in this particular case is going to be 1. And what is anything times 1? Itself, right? So what we get is we get x times y. But now we can substitute this equation in. We know that y times 1 is certainly the same as y. Everyone agree? So what we do is we substitute, instead of writing y, let's substitute y times 1. And that's certainly the same thing as y. So we've rearranged the parentheses to where they were originally on x and y. But since z happened to be 1, we were able to absorb the 1 using the laws of multiplication and then rewrite y as y times 1, just using the simple fact that y is y times 1. We've shifted the parentheses. Okay. Now we've shown that M is not empty. It includes the number 1, right? Now what we'll do is we'll say pick up any number from M. And we want to check, is the successor also in M? I like this little proof here. You're going to like it too. Okay. What do? We say, I'm going to take xy times z successor. And what was the definition of multiplication? It said if you have a successor like this, and you can rewrite it as xy times z plus one more copy of this. Everyone remember the definition of multiplication? Think of this as z plus 1, right? What this says is that you have x times y copies. Sorry, you have z copies of this, and then that successor says take one more copy of that. So you have z copies of xy, and then the successor says take one more copy of xy. Okay. Recall the definition of z. It was an element of M, meaning it's an element where you can shift the parentheses, right? So we go ahead and do that. We can rewrite the parentheses here. Sorry. Rewrite the parentheses here. And now we notice this common factor x. And we proved in the last class that we have a distributive law. It says you can move things in and out of parentheses. That x will factor it out. We get yz plus y. And going back to that definition of multiplication, remember, this says we have z copies of y, and then we have one more copy of y. So how many copies of y do we have?
2.
We have z copies of y here, and then we have one more in addition to that. So we have
2z.
z successor copies of y, right? Yeah, we have z copies here, and then we have one more copy. So we have z successor copies of y. But what did we do? We worked through the act of moving the parentheses from the left two terms to where they're now grouping the right two terms, and that's exactly what we needed to show. So we see the associative law holds, right? We've got 1 as an element where it holds, and all successors satisfy that requirement as well. So the inductive hypothesis says if 1 is in there, and all successors are in there, then M is all natural numbers. Be honest, you liked it. All right. So that's the last pretty proof. The last one that's like enjoyable. The next are like, oh man, do I have to? They're not difficult, it's just like, eh. So we have theorem 32. these are the types of properties where it's like, you don't need anyone to prove it to you. They're pretty believable. So what we're going to do, we're going to prove B, and then we're going to prove A, and then part C will be a homework problem. So for part B, we say, let x equal y. We're going to substitute this into the equation xz equal to xz, right? We start with something that we know is absolutely certain. Xz is certainly the same as xz. And if x is also the same as y, then we can substitute y wherever we see an x. So we get xz is equal to yz, because we replaced x with a y.
What's that word?
Equation.
Oh.
So you can just substitute with that word?
Yeah, because they're the same, right? So if you had 5, you could certainly replace 5 with 2 plus 3, right? Anywhere you see a 5, you can use a 2 plus 3. So that's what we're doing here. Is since x and y are the same, anywhere you see an x, you can put a y. All right. So for part A, we're saying suppose that x is greater than y, then when we multiply a natural number on both sides, we maintain that inequality, right? So this goes back a couple weeks ago, but what does it mean that x is greater than y? That's what we need to prove. What's the definition? What does it mean for x to be greater than y?
About a little bit more.
Yep.
Plus a little bit more.
Exactly. X is equal to y plus a little bit more. And so, if this is true, then this equation is guaranteed to hold for some u, right? And so what we'll do is we'll multiply both sides by z. So we get xz is equal to y plus u times z. And we have this nifty gadget called the distributive rule. So you can distribute the z through. And that's it, right? That's all we needed. Now we see that xz has to be larger, because xz is equal to yz plus a little bit more. So that says that xz is greater than yz. And like I said, I'll leave part C for you guys to do in an assignment. Most people can see how to do it already. Right, you've got, if x is less than y, that says y is equal to x plus v. Multiply both sides by z, distribute. Right. you have any of these three conditions, then what can you say about the relation between x and y? Here?
So x is equal to y plus u?
That's true.
Okay.
But the inequality that we're going to recover here is that x has to be greater than y. Okay. There's an equation that we're going to recover here. X is equal to y. And if this is true, what's the relation between x and y?
X is less than y?
Yeah. Now what's interesting about this proof, in Landau, he says, it follows theorem 32, sets blah, blah, blah. He doesn't really work through it. I was a little bit, I wouldn't say stuck on the additive version of this. So if you think back to the additive version, it says if x plus z is greater than y plus z, then x had to be greater than y. Everyone remember that? So in additive versions of these, I basically cooked up a proof where we used subtraction without ever using subtraction. Because we haven't defined subtraction, we've only defined addition, right? And this would be really, really easy if we could just, you know, in this case it would be divide by z. We don't have division, so we can't do that. So in the previous section when we were talking about addition, I cooked up my own proof, finding a way to subtract without subtracting. And Landau had this comment here that, you know, it follows pretty much automatically, so, you know, just, you work through the proof on your own, it's pretty much automatic. And I was thinking about it, and I couldn't see exactly what he was getting at. And I think he's talking about proof by contrapositive. Okay? So, as I was working through the proofs for these, here, I was thinking that it must be contrapositive what he was talking about. So we're only going to prove A. Assume for contrapositive that x is less than or equal to y. Okay, because think about contrapositive. It says, if P then Q is what you're trying to prove. Contrapositive says, show that whenever not Q, then you know not P, right? So we take this ending statement, Q, and we negate it. What's the opposite of x being greater than y? Yeah, if x is less than or the same as y. That's the negation of that statement. So this is the statement, assume not Q is true, right? Then by the previous theorem, theorem 32, we would have xz less than or equal to yz. And that's it. That's the proof by contrapositive, right? It says, if P then Q is what you're trying to prove, and if you prove not Q implies not P, then you're done, right? So what did we do? We said, here's not Q. And if you have not Q, then apply 32. That says that you can multiply both sides by z. So you multiply both sides by z, you maintain that inequality, and what do you find? You find not P. So if not Q, use what we know about that relation, and we find that not P had to be true. Therefore, contrapositive guarantees that this if P then Q statement will also be true. Okay. So we won't go through the others. Any questions on that?
How do you know when you contrapositive?
Whenever you're in the mood. Yeah, no, that's literally it. So there's lots and lots of different proof methods that work. And so if you find that it's easier to use contrapositive, then use contrapositive. So let me put it this way. If it's more natural to say, what happens if something fails, then that might be a good way to use contrapositive. So, yeah, exactly. So you're saying, you know, suppose that I want to prove that an even plus an even is an even, right? You say, well, gosh, I don't know. I mean, I could do it this way, I could do it that way. What would happen if I didn't have an even sum? Well, that would mean I would have to have added an odd in there. So, you know, when you start naturally asking, what would happen if the conclusion fails, then that's a good time to use contrapositive. All right, so the other examples follow pretty much identically to this. So we'll move on. If x is greater than y, and z is greater than u, then x z is greater than yu. If you like thinking in terms of that vertical notation, we're just going to multiply straight down, right? X times z is going to stay larger than y times u. Just multiply both sides together and you maintain that inequality. What's a number system where this property would fail? If you have a 0, yeah. If you have a 0, this could fail. Because if you have 0 is greater than -1, and 5 is greater than -3, multiply both sides together, you get 0 greater than -1, and -3 would multiply out to +3. And 0 is not greater than +3. So if you have negatives and if you have zeros floating around, then this property is not equal. We're only looking at natural numbers, right? So that guarantees that it always holds. So, let's go to, we're so close to finishing Landau. Let's go ahead and prove this. What does it mean that x is greater than y?
Y plus u.
Yep, y plus a little bit more. Now we're using the variable u already, so we're going to give it a different name. We'll call it y plus a. X is y plus a little bit. And what does it mean that z is greater than u? It says z is equal to u plus a little bit more. Then all we want to do is we want to establish this inequality, right? So we just multiply x and z together. X times z is the same thing as y plus a little times u plus a little. And now we have a set of parentheses. And many people might start thinking FOIL, right? First, outer, inner, last. What's the rule that goes into that law, though? What makes FOIL work? Yes, distributive law. So what we're going to do, we're not going to FOIL this. We're going to write it out piece by piece and use the distributive law properly, like algebra students don't. So distributive law says if you have a number outside of parentheses, we distribute it through. So we're going to treat this like one single number, and let's distribute it. So there we go, that distribute it to the y, distribute it to the a. We get y times this number, plus a times that number. And then we've got another set of parentheses here. We'll distribute through those. So y times u, y times b, a times u, a times b. And this is the thing that we wanted to somehow generate. That y times u term. We notice that xz is equal to yu plus a whole bunch of other numbers, right? So what that says is that to get from yu all the way up to this number xz, you have to add all three of these terms to it. Okay. And so that says that xz definitely has to be larger than yu, because to get from yu to xz, you have to add this set of numbers here. So therefore, xz larger than yu, which is what we wanted to establish.
Why do you put a yu on a difference?
Because the inequality that we care about is we want to show that xz is larger than yu. So we want to show that to get from yu up to xz, you have to add numbers to it. So we have this thing on its own, so that you say yu plus this number gives you xz.
Even adding all of that, yu is still smaller than, it's smaller than this. So
Yeah.
you do all that just to prove that it's smaller,
Yeah.
regardless of adding all those other things to it?
Exactly, yeah, because what you're doing is you have the definition of less than. It says, to show this thing is larger than that, you have to say that this thing, you need to add something to it to get xz, right? So the crux of this proof just says, I'm going to rewrite xz in terms of y and u. And then I'm going to extract the y and the u term from it, and we'll see that to get that yu term up to the xz term, you have to add this collection of numbers here. And that's exactly what the definition of inequality says. It says this number is smaller because you have to add something to it to get to xz. Okay. All right. If x is at least y, just make sure I have this set up properly. So 30, around 35, is that right? So 35. If x is at least y and z is at least u. That's our gradient. Then xz is greater than yu. And then they have another case here that if x is greater than y and if z is at least u, then that inequality will hold as well. We're only going to prove the first case. So all we're going to do is let's go ahead and write xz in terms of these inequalities here, okay? So we note that z is certainly equal to u plus a, because we have that strict inequality that says that to get to z from u, you need to add something. And what we have is that xz is the same thing as x times u plus a. Distribute that x through, we get xu plus xa is equal to xz. And so what that says is that xz is going to be greater than xu. But we have an earlier theorem that says if you have the same number on each side of an inequality, then that guarantees that that same inequality holds for the other two numbers. So z and u have this relationship. From here, let's go and recall that x was at least y. So what we'll do is multiply the right-hand side by y. And the left side by x. And so we're basically doing this maneuver here. Remember how we sometimes stack these things vertically? We're saying, we know x is at least y, and we know z must be greater than u. So we just multiply these things together. Xz must be greater than yu. So the last theorem, theorem 36. X is at least y, and z is at least u. Then xz is at least yu. And this basically follows from the previous theorem. something went wrong in this proof, right? Yeah. Something went wrong in this proof. So let me give you the proof that I wrote up in my notes. That is, I know that this proof is correct.
So 35 lines.
Yeah, 35. I ended up making it look like kind of a cyclic argument there. So let me.
Cross that.
Yeah, that's the same thing. So 35. If x is at least y, then z is greater than u. Then xz is greater than y. So, we certainly know z is the same thing as u plus v, because we're told that z is greater than u. Now we have x is at least y, meaning that one of two things must hold. Either x is greater than y, or x is equal to y, right? That's what that definition means. Either x is greater than y, or equal to y. So we're going to split this up into two cases. And let's consider the case that x is equal to y. Then what we'll do is we'll multiply both sides here by x. We'll distribute that x through. And just like we did before, if x is equal to y, we can make a substitution. In this x right here, we'll substitute a y. Okay, here we see an x, we can replace it with y. And that gives us what we need. We need that xz is larger than yu, which we now have because xz is equal to yu plus another number. Case. The second case says x could have been greater than y. Okay. But in this case, theorem number 34 holds. So we don't need to reprove anything. In theorem 34, we said if x is greater than y and z is greater than u, then you can prove that xz is greater than yu. So since we've already proved that, we can now just apply that theorem that says, yeah, x has to be greater than y. Sorry, if x is greater than y, then xz is greater than yu. All right, so that is 35, and then theorem number 36. Basically the same thing, right? You have a couple different things that could happen. X could be equal to y, and z could be equal to u, in which case we proved a couple pages earlier that you can multiply the two sides and maintain equality. Or you could have that x is greater than y, greater than or equal to y, and z is greater than u, in which case that part of theorem 35 holds. Or you could have that x is greater than y, and z is at least u, in which case the second part, which we didn't prove, but it's basically the same proof, the second part of theorem 35 will hold. And so this one we don't need to reprove anything, we just get to apply proving theorems. And that is sort of the point of Landau that I'm trying to make, actually, is that math builds on itself. We start at that foundation of definitions, right? We have to define this thing called one. We have to define this thing called a successor, all that stuff. And so you start with those definitions, and then the axioms tell you what relationships hold between the things you've defined. So we have an axiom that says we have a successor. We have another axiom that says nothing succeeds to one. We have another axiom that says if one is in there and all successors are in there, then you've got all natural numbers, right? So from those axioms that relate the different things that you've defined, you then start to derive theorems. And then as you proceed, those theorems, you get to start using those theorems to prove other theorems. And then you use those theorems to prove other theorems. And so anything that you do in math, you've got like umpteen million different things that came before it that you had to prove to make sure that what you're doing is legit, right? So if you think about the quadratic formula, negative b plus or minus square root of b squared minus 4ac all divided by 2a. You've got tons and tons of crap that went into this that you have to establish first, right? And so that's what Landau did, is he said, if you think back to the preface, when he was talking about his daughters, my daughters have been studying chemistry for several semesters, think they've learned differential and integral calculus, yet they don't even know why the commutative law holds. So he goes all the way back to the beginning. He says, let's start at the Peano postulates, those 5 axioms. And then from there, that's where you get all the laws of algebra. And from those laws of algebra, you start deriving more and more theorems. And so this quadratic formula, for example, you know, go through tons and tons and tons of different hoops, but eventually you get there. And you know, it's completely solid. It's set in stone. It'll hold for all eternity because it was derived from first principles, right? So, congratulations on making it through Landau. And so, I don't have anything further for today.